Righty, hi everyone. I'm Andy Trafford. I'm doing research in distributed acoustic sensing, which basically using fibre optic cables for seismic surveys. I'm a geophysicist, and so I'm just going to give you 10 minutes on my research and how it's applicable to offshore. So I suppose just to start off with, distributed acoustic sensing, many of you might not be aware of what it is. What we do, we use a standard commercially available fibre optic cables, and if you impart a strain on that cable and fire a laser down it, you can measure the strain. So we look at nanostrain, a very sensitive method of measuring acoustic signals. On the research, we had 3 test sites, one in Blessington, Sand Gravel Quarry, intertidal zone, Dublin Strand, and then we did some offshore trials last summer in Dundalk Bay. If I just give you a quick overview of what it was we're trying to do. As with this research, it's relatively new using fibre optic cables in this way. It's been used for downhole surveys in the past, but for using it for surface wave measurements, it is relatively new. So we had to do some validation work, and that was what we did in Blessington Quarry. So here we have some shot records using geophones, and then the comparable one using DAS. One of the main benefits of using acoustic sensing in this way, fibre optic cables, is that you're not limited with the number of sensors. Typically you'd have hydrophones or geophones at set intervals. With this, we use the whole of the glass fibre core as a sensing element. So we're not really limited practically with the distance we can look. I'll show you later. We've used up to 1 kilometre long cables for the research, but we're not limited to that. So at Blessington, we carried out, and we did some other geophysics methods, ERT and radar, just to validate the method, and we can see here that we get comparable data with both systems. The intertidal zone we chose was Dublin Strand. One, we'd done some work there previously with GSI for a master's project in 2016. It's a gently shelving, large intertidal site. And what we were able to do, the reason for doing this on an intertidal site is that we have, again, very really important, we validate our results. So we've got high water, we can do a marine survey, and at low water, we can do a comparable survey on land. So just a quick schematic of the setup. We house the control unit in a van at the beachhead. We used a small landing craft to deliver the cable to the beach, and then we deployed a kilometre of cable perpendicular out, and then we fixed it with just a clump weight and a buoy out at sea, and we used a smaller vessel as a gunboat for doing the marine airgun shots. If we just have a look at some of the fibre optic data. So one of the other things about this is that we record continuously, so it's a monitoring system rather than a shot. This is 20 minutes of data speeded up. Each of the horizontal lines there is a shot at different points along the cable. 0 is out at sea, the last 900 to 1,000 metres is the beach, which is a bit noisier. And we can see these sloping events here. These are ocean waves travelling, propagating towards the shore. So we can pick up the pressure from the ocean waves as well. If we have a look at this in more real time, so the vertical lines are the sloping lines, that's just the waves coming in. You can see the individual footfall on the beach with someone walking down the beach. And then this is a mid-shot using an airgun. So the information we're interested in is this fan of seismic data. It's a surface wave, interface wave. We isolate that, and then we produce a normal shot record. You could do the same thing, but you would need to have, for this record here, we'd need 500 hydrophones, all a metre apart. So it gives us a lot more data and it's a lot quicker to collect. If we just look quickly at some of the processing that we do of the data, we take the shot record and we convert it into a frequency domain, and this allows us to look at the surface wave detail. And it's this information here, which, as Mark alluded to before, allows us to derive the shear wave profile in the ground. We use Monte Carlo method, mathematically model the inversion, and we can produce a shear wave profile with depth. With a fibre optic cable, what we do, we take shots at set intervals, so we can produce 2D profiles relatively quickly, and this is one of the massive advantages over using fibre optic cables than traditional seismics. Typically every 25 metres we would take a shot and we produce a 2D surface wave profile. This profile here shows how we've got different stiffness in the ground down to about 20 metres. But the thing with it, this took about, once the cable was on the ground, took about 45 minutes to collect it. So the speed is actually the key factor to this. And especially when we're looking at offshore work, we tend not to get massive weather windows. So optimising what we can do is very important. From an academic point of view and a confidence point of view, we have to compare data from different sources. This is the data using fibre optics, hydrophones and geophones, because we were on the intertidal zone. So with the fibre optics we're measuring strain, with the hydrophone we're measuring pressure, and with the geophone we're measuring vertical displacement. It doesn't really matter to the engineer. What matters is it gives us the same result. So basically we're just validating the method against what would traditionally be used. So we learned quite a lot from the intertidal work. We then went offshore, and I suppose this is the bit that shows where iCRAG works as an organisation, because you're not doing your research in isolation. We had 10 days on the Voyager. We deployed ocean bottom sensors. We had absolute pressure sensors from DIAS. We had the Sparker from the GSI. You see the Marine Institute are involved there. We're collecting gravity cores. We get a whole lot of data that we can combine. The setup on the Voyager was very similar to what we would have done on the beach, other than having the van at the beachhead. We've got the Voyager acting as a control vessel, and we deployed 1,000 metres onto the seabed. We've got a source boat with an air gun, radio trigger, USBLs for positioning from the Marine Institute. So it's quite a complicated survey design, but it all comes together at the end. And also, because we've got Sparker data, we have the layering, which we can then overlay our data onto. So, as with a lot of the research work, this is the beauty of doing the research, I suppose. You're not down a straight line. There's other things that come out of this. We had absolute pressure sensors fixed to the cable on the seabed, and this is the data from the pressure sensors. If we have a look at the fibre optic data, the DAS data, we've got close to 3 hours of recording here. The top hour and a half is passive, no shots fired. The bottom, each of the horizontal lines is an individual shot. But these sloping lines here, I think we're in about 25 or 30 metre water depth here. And these are ocean waves. So what we can actually see, if we zoom into here, we can see that we've got the sets of ocean waves passing along the cable, along the full length. And we can tie that into absolute pressure changes. So the reason this slide's here is where we go in with this research in the next phase is looking at how these pressure changes vary with regard to sediment mobility. So that's one thing that's come out of it with having the collaboration with the DIAS supplying us extra equipment. Something else that came out of this is something we want to explore from an environmental point of view as well, because setting off air guns causes problems with licenses and in areas of SACs. So this is an example of a shot record. All this data up here, as far as we're concerned, is noise. It's the noise an air gun makes, it's the sound that travels through the water column. It's of no use to us at all. What we're interested in is this data down here, these sloping lines. This is our surface wave data. What we did, we had the fibre optic cable laid on the seabed, and we were taking gravity cores. So we decided to listen to what the gravity core sounded like. And that's what a gravity core looks like compared to an airgun source. Basically, we get no energy transmitted through the water column. So it throws up a whole new avenue of research in can we provide more environmentally friendly sources to get around the problem of using air guns. So again, that's something we want to look at in the next phase of the research. We did work on different geological settings, so you can see that we get different characters of these. And again, I don't want to, this to me is incredibly interesting, probably to 90% of you. It doesn't mean anything, it's not really exciting, but I could talk about this slide for weeks. But basically what we get in, we have a thick mud site on the top and we have a till site on the bottom. This signal here is the mud, and this is what we get from the till. And basically it's just to illustrate that we can map different subsurface properties using the surface wave method. And also, because of we have a lot of CPT data, previous data, we can correlate it to different to CPT work that's been done in the past. And again, there's quite a lot of work to be done on that. 2 minutes, thank you. Preempt you there. So, I suppose where is this all leading? We can collect Sparker data. Sparker data is brilliant. It gives us a really good picture of what's going on under the seabed. It doesn't give us any geotechnical information. So we've got CPTs, which give us a pinprick in the ground, and we can get cone resistance and pore water pressure, so really valuable geotechnical information. When we can then apply seismic at a bigger scale, we can tie all these things together. So we've got a shear wave profile there, I think it's roughly 700 metre long shear wave profile overlaid onto the data, onto the Sparker data. So as well as getting the layering with the layer thickness, we're also getting geotechnical properties over significant lengths. So that's the last slide on the previous project. So where this is headed, because we're looking at fibre optic cables, we're looking at strain. So strain and sediment mobility are intrinsically linked. So for our next 3-year project, the first phase we're going to be doing some baseline studies on areas where we've got higher energy environments, more sediment mobility. Dundalk Bay was perfect sounding ground to do the work, but it's quite a low energy environment. So we're looking at something, a sand type probably off the east coast. We're then going to do some physical modelling, some scale modelling with wave tanks, and this is with a view to looking at scour monitoring and assessment using fibre optic cables. And in the 3rd year, hopefully, we're going to be deploying this on a live site, because one of the impacts of construction in a marine environment is that it alters the ground, the construction itself, as well as scour, but also on the actual stiffness of the sediments. So that's the next 3 years for me. So I would, so if you have any questions, that would be great. Thank you.
Hello. Hi. I'm Clytus from Photonic Systems Group in Tyndall. So in terms of the fiber optic technology, I'm assuming you're using commercial equipment. What would be the limitations you're seeing currently? Is it the resolution, or is it the range, or are you able to cover all the acoustic frequencies of interest?
That's a good question. So, resolution is comparable to using hydrophones. We lose a little bit on the high-end frequency, but not what would affect the resolution, because we're looking at we're looking at shear wave profiles with depth. So we're still able to record the high frequencies. The systems are incredibly sensitive. You can record up to kilohertz with them. Obviously, we're not. We're talking about the tens of hertz range, so that's fine. The range for the next phase of the project, we're looking at deploying a 5-kilometre cable. But with the latest hardware, we're actually putting a cable out on a railway site in the UK, where we're putting in a 10-kilometre long cable. And with that, we can record, it's called optical channel pitch. Basically, each channel, the channels are 1 metre spaced. So for a 5-kilometre cable, we'd have 5,000 channels. So the data quality isn't as good as if you had 5,000 hydrophones, but 5,000 hydrophones will cost an awful lot of money. So we have a data redundancy in there. But also the exciting thing for the next phase is that we're looking at measuring strain as well on the seabed. So as well as being able to pick up acoustic signals, we can measure lower frequency strain as well. So there are limitations in body wave. So if this could record reflected signals as well as hydrophones, this would have been developed a long time ago, but they don't, because we're measuring longitudinal strain, whereas a reflection survey would be measuring a vertically travelling body wave. So that's why. But for surface wave, interface wave determination, it's a perfect tool for that. So. Thank you.
Thank you, very interesting talk. Why did you mention that the data quality of the DECC cable is lower than if you have, for example, 5,000 hydrophones? Is it due to the sensitivity of the cable? Thank you.
It's due to, well, they're measuring different things. The hydrophone, obviously, it would measure the pressure changes, whereas we're measuring strain. So we're measuring different things for the first part, but also the way in which it works, we measure along what's called a gauge length, so a certain length of the cable. So the way we have it set up is about the shortest gauge length we can get with the system available, which is 2 meters. So we're measuring the acoustic response of a 2 meter length of cable. So there is an element of averaging. In the same way as which a traditional hydrophone cable has a group of hydrophones. But it works in a negative connotation for what we want, because we're averaging, whereas for traditional reflection work, that's what they want to do. They want to average to get rid of certain noise, and it's that noise which is the surface wave that we use. So.